I'm just going to go through practicals A, B, and C through the assessment or the bit of paper that you're going to submit to me, and then I'll go through and do the recording of the actual practical. So practical A is the Bernoulli's theorem. So what you need to do is on the first page, I need your name and student ID. Alright, come on down to the second page. We have an objective of the experiment. Alright, what we're trying to do is investigate the validity of Bernoulli's theorem. So under point 2, we've got some equipment. So for this one, what we need to fill out is we need to fill out the cross-sectional area for each point. So A, B, C, D, E, and F. We need to work out, we've got the diameter, so we need to work out the cross-sectional area. So remember, the area of a circle is pi d squared all over 4. Alright, so you're going to use that for each one. So for point A, so A is 25 millimeters. So our area is going to be pi by 0.025 squared all over 4. And whatever that equals to be, you'll just put here. Okay, so for each one, for all of the corresponding diameters, you'll write the cross-sectional area next to it. So moving on down. Alright, we've got a bit of theory here. So this theory we've gone through before. Alright, so it shouldn't be anything unusual or anything new. I'll explain a bit of this as we go through the practical. This is the basic setup of it. So A is this piezometer here. B, C, D, E. Alright, we've got F and G over here. So I'll go through this when it's all set up, but this is a schematic of it. So obviously we have some flow, which is our V dot, which is our Q. So flow runs through it. Remember, taking from the middle point, then our piezometers register a pressure reading through it all, which is what we expect. We expect at the venturi or the throat, as the pipework seems to neck or gets smaller in diameter, we expect our pressure to decrease as our velocity increases. So we've gone through this a few times in class. This should make sense by now. Alright, again, running through a bit more theory in here. Alright, rearranging formulas and understanding it all. Procedure, so how we go about the actual practical. Alright, nothing to do here. Results. Alright, so cross-sectional area, pi d squared on 4. So in our results page, you need to put one sample calculation in here. Same with the volumetric flow rate, velocity, velocity head. Alright, I'm not certain as to why I'm getting these here, but it should appear correctly on yours. If it doesn't, please let me know. Okay, so what do we have to do here? This is where we start. Alright, this is the important bits here. So filling this out, cross-sectional area. So diameter, pi d squared on 4, gives me this area. Do it for all of them. So we fill in through here. My flow rate is V divided by T. I know my volume for test 1. Volume is 10 liters. Second, or my time, 57 seconds. So quite simply, I would come through and go flow rate. So flow rate, which is V dot, which is Q, is equal to volume on time, which is 10 divided by however many seconds I have here, 57 seconds. Alright, divide the 2, what do we have? 10 divided by 57. Alright, 0.175 liters per second. Alright, convert it across to meters cubed. Alright, so times by 10 to the negative 3, and you should get that one going there. Velocity, V is equal to Q on A. So, sorry, what we will do, V equals Q on A, we've just calculated Q or V. So I need to bring this to meters cubed. So times 10 to the negative 3 brings that to meters cubed per second. This becomes a lot smaller. This is our flow. Divide flow by the area which we calculated before, and you get your velocity. Okay, so quite simply, start with this one, work out your area, work out your flow using these numbers, V and T. Make sure you convert it to meters cubed per second. Get your velocity, which is V dot on A, or Q on A. So this number here divided by this one here will give you this one in here. Alright, now what do we have is I have to work out my velocity head. So how do I work out my velocity head? What is it? So remember our velocity head, so hv is v squared on 2g. We've just calculated v. Alright, we calculate our velocity here. So whatever number we have sitting in here, square it, divide it by 2g, that appears along these lines, and then simply add them together. Pressure head, HP, is in this line, and HV we find in this one. Add them together, and you can solve through here. Repeat the same process for test 2. Alright, so mine I have not come across very nicely at all. So what I'm going to do is I will just graph these on the whiteboard. So what your prac is going to ask you to do, it's going to ask you just to graph what we've found. Okay, so you have each point A, B, C, D, and E on the graph, and we need to come through and do a graph for them. So I'll sketch it up here now, and it looks something like this. Alright, we have like this. This is my head in meters. This is point A, B, C, D, and E along the graph. So this here is going to be in your in the Word document. So for the practical, alright, just because I brought it to PDF, it's just kind of skewed it a little bit. But A is down here, B, C, D, and E are down this side here. And what we'll do is quite simply, wherever the head of A is, going from what we've calculated, so the total head, we've got for A, we've got for B, we've got for C, for D, for E. We just plot them along here as to where they sit. So A might be here, B might be here, C, D, and E. Alright, once we've got them, what we do is we draw in a line of best fit. It's better to use Excel if you can. Alright, it will plot the best line of best fit for you, but we'll come through and we'll end up with a line, something like that, plotting them all together. Okay, so this is what we're going to be looking at. Alright, so this is what we can gather from the information. Now, that solves this first part. Then what we have is we've got a few different things here. So comment how well the calculated total value head agrees with the measured values. Alright, so we can calculate it and we can measure it. So I have a calculated value in here, and I have a measured value in here. Talk about the difference between the two. Why do we get a difference? Where do they come from? All right, some possible reasons. Okay, come through and just write these out. This is just explaining or concluding the experiment. All right, very important that you're able to interpret the data and put it back into technical knowledge. Practical B is losses in bends. All right, this one's not too difficult. What we need to do is we'll go through it again, just like last time. Student name, student ID. We've obviously got the objective of the experiment. We're trying to verify that head loss in bends are proportional to v squared on 2g. And we're trying to determine some constants of, or the k factors for different fixtures. So short band, elbow, valve, miter, control valve, long band, sudden enlargement, sudden contraction. So this is a schematic of how it all looks. All right, we hook piezometers up to where the water or the fluid is flowing through, and we gauge our pressure readings from here. So not much to do to start off with. We've got theory we've got to look at, all right, but we've gone through this previously. For this one, this formula here is required. You will need to use it. So procedure, all right, just going through how we can actually do it, which I'll go through in the next recording. Now this is where we start. All right, what we need to do is volume. So I've got my volume in liters, have to convert it to meters cubed. So remember, liters per second to meters cubed per second. We times by 10 to the negative 3 or divide by 1,000. So that's all you do there. You just divide 5 by 1,000 and get it into here. Again, flow is the volume. So volume divided by time. It's time here. So get this volume divided by the time, you'll get flow. Velocity is then flow divided by area. So you have to come back, calculate the area. All right. Have a look up through here and you'll find the areas of different things. So make sure you read through it and you can go from there. All right. And then we calculate our v squared on 2g. So I've got v, I can then calculate my v squared on 2g. So what do I need to look at next? Well, I've got published k factors here. I need to find my k factors for the experiment. So how do I find them? Well, for this experiment, what you can see is if I plot the change in head versus the velocity head, this line here, all right, the tangent of this line is actually our k factor. So the slope is the k factor. So this is what I need to do. So you can graph it. It's up to you. You can graph it or you can just do it numerically, which is probably what I would do, is do it numerically. So I know my delta H because I'm given it for all cases. And I know my v squared on 2g. So for this one, what I would do, I'll get the first one done for you. So the miter, delta H is 0.082. So my k factor is equal to delta H on v squared on 2g. So for k equals 0.082 all over v squared on 2g equals whatever it is. Okay, so this number here divided by this one gives me this, and so on and so forth. So the difference is simply this subtract this. All right, so what's published versus what you found, and then our residual squared. So you guys should be able to do this. You should have learnt this in maths. Okay, put it in Excel and Excel will punch it out for you. Now we've got to do some graphs here. All right, the graphs are not too bad. Graphs are actually fairly straightforward. You're just inputting all of the data sets that you find. So 1, 2, 3, 4, 5 versus 1, 2, 3, 4, 5. So how's it going to look? You'll simply graph. If I'm looking at the elbow, this is the elbow, graph delta H all over V squared on 2G. You have 5 points. Okay, 1, 2, 3, 4, 5. So 5 points that we need to look at. So let's say we've got 1, 2, 3, 4, 5. We'll then have a line of best fit running something like that. Alright, this is how it should look. And you'll do that for all of your numbers. So 5 of them for the miter, 5 of them for the elbow, 5 of them for the short band, long band, contraction, enlargement, you keep going. Okay, that's what it's asking you for here. So it's a simple plot, nothing too difficult. So you can either do it by hand or you can do it on Excel, it's up to you. Alright, a couple more conclusions. So make a few comparisons and comment on some relationships. So practical B, fairly straightforward. Practical C is our system resistant curves. So our objective, or the object of the experiment, we are investigating the system resistance curve relationship of a pipe and valve fitting system. This is what it looks like. Alright, it's the same setup as last time, but now we're going to be looking at a few different things. So we've got Miss Bernoulli's theory, which we've been looking at. Alright, I will go through this, like I said, I'll go through this again when we do the practicals, and when I do the pracs. But for now, just follow me through here. So we've got a bit of theory here. This is what we looked at in our pump section. Alright, so obviously we're looking at a pump. Static head, dynamic head. So static head is the elevation head and the pressure head. Dynamic head is due to the velocity. Alright, and we expect the valve's fully open, something like this. If we start to close the valve, we get more losses, so we get a nice sharper curve because our K factor increases. Alright, K factor increases, and same with the V. We've got the procedure again, some more results. This is where we start to look at. So our flow rate. Alright, how are we going to work out this? Don't know why it's come up. Our flow rate is in liters per second. So volume, time. So I know my volume, I know how long it took. Divide them by each other. Okay, so 5 divided by this will give me my flow rate in liters per second. My potential head, H2 take H1. Alright, this will make sense tomorrow when we go through it as well. Okay, but the elevation difference is going to be taken as 0. So potential head 0, 0, 0, take H2, take H1 equal to 0. Now my target system head given to you, HI, H0, subtract them, so this subtract this comes here, and then my total system head is this plus this. In our case, this will be 0, so it would just be this one in here. Okay, repeat it again, doing the same thing with this section here. So this one's got fittings with 3 closed turns, and this one's fully open. So what we need to do next is we'll plot a system resistant curve. So how these are going to look is what we'll be logging or graphing is we will, on another plot, what are we going to plot? We're going to plot our total system head all over our flow rate. Okay, So if we come back and look at the theory, I have head and flow rate. So I need to switch my graph around. I have my head on one side, my flow rate on the other. So let's come around and let's flick that around. So head, or total head, my flow, and then we'll plot the points that we find. So we'll have one something like this. They're fairly curvy, something like that roughly. Then I'll have another one in green that might sit something like this. Basically, we're going to end up with two plots side by side, looking something similar to that. Okay, where what will happen is this here will be fully open. This one here will have 3 closed. So that's roughly how it should look. It's better that you graph them both on the same graph. That way it's a lot easier to compare. Okay, so have a look, have a read, and plot your graph in here. You can do it by hand, it's up to you. And again, we just got some conclusions to go with. So comment on the relationship, comment on the effect, and discuss your results. Okay, so straightforward, that's how we run through our the paperwork side of things, and I'll go through and do the recording for the practical. So you get to see me tomorrow going through it all. Thank you.